The 6,000 Newton beam shown below is being held at rest by the crane. What is the tension in the horizontal cable, and what is the compression force in the boom? We draw the force diagram. We note that we have three concurrent forces at a particle at this point. This is the tension force exerted by this wire. This is the boom force acting on the particle in this direction, and this is the weight force, which is the same force as the weight of the beam, which is given. We redraw our force diagram with the particle at the point of concurrency as the origin of our new coordinate system. This is the x-axis, this is the y-axis, this is the boom force, this is the weight force, this is the tension force. We now go through the problem-solving process. The givens. We're given that the magnitude of the weight vector of the beam is 6,000 newtons. We draw a line at the point of concurrency of the three forces parallel to this line and extend the boom force vector. We see that this angle theta is the same as this angle theta, and that angle is 20 degrees. That gives us this angle theta in our force diagram. The unknowns. What are we looking for? We need the magnitude of the tension vector, f sub t, and we need the magnitude of the boom vector, f sub b. The equations. This system is at rest, therefore it is in equilibrium. Therefore we write the equations for equilibrium in two dimensions. The net force, or sum of the forces in the x direction, is the x component of the tension force plus the x component of the weight force plus the x component of the boom force. These all sum to zero. Likewise, the net force in the y direction, which is the y component of the tension force plus the y component of the weight force plus the y component of the boom force, all sum to zero as well. Substituting, first of all, symbolically, the net force in the x direction. Ft of x is minus the magnitude of the tension vector. The tension vector is out the negative x-axis, plus the x component of the weight vector. The x component of the weight vector is 0 since the weight vector is out the negative y-axis, plus the x component of the boom force vector. That's the adjacent side of this right triangle, and therefore it's a form hypotenuse times the cosine of the angle. Therefore, that's the magnitude of the boom force, that's the hypotenuse of this right triangle, times the cosine of theta. These all sum to zero. Substituting in numerically, we have minus the magnitude of the tension force plus 0.0.9397 times the magnitude of the boom force is 0. This is one equation with two unknowns. We need to write the other equation. For f net of y, we get the y component of the tension vector is 0 since it is out the negative x-axis, plus the y component of the weight vector. That is minus the magnitude of the weight vector since the weight vector is along the negative y-axis, plus the y component of the boom force vector. That is the opposite side of this right triangle. The right triangle has a hypotenuse, which is the magnitude of the boom vector. Therefore, the y component is hypotenuse sine of theta, or the magnitude of the boom vector times the sine of theta. This is all equal to 0. Substituting into the y equation, we get minus 6,000 newtons. That's the weight of this beam, plus the sine of 20 degrees. That's 0.3420. So we get plus 0.3420 times the magnitude of the boom force is 0. We now have two linear equations in two unknowns. The next step is to solve this 2 by 2 linear system of equations. Looking at our 2 by 2 linear system of equations, we see that the second equation only has one unknown, the magnitude of the boom force vector. Our strategy is to solve this equation explicitly for the magnitude of the boom force vector, and then substitute what we get into this equation and then solve for the magnitude of the tension force. Algebraically rearranging the second equation to solve for the magnitude of the boom force vector, we get that the magnitude of the boom force vector is 6,000 newtons divided by 0.3420. That gives us 17,544 newtons. We now substitute that value for the boom force vector magnitude into the first equation. This gives us that the negative of the magnitude of the tension vector plus 0.9397 times 17544 newtons is 0. Solving that for the magnitude of the tension, we get 16,486 newtons. We are now ready to state the answer to the problem. This is a 3 significant figure problem. Therefore, we must report only 3 significant figures accuracy. buoyancy. The magnitude of the boom force vector is 17,500 newtons, and the magnitude of the tension vector is 16,500 newtons.